In this video, I am going to prove the formulas for the sum of an arithmetic sequence and of a geometric sequence. It's not like you can't solve the problems involving sums if you don't know where the formulas came from. In fact, you can do that because the formulas are right there in the formula booklet. But I always think that you can do a little bit better if you understand where the formula comes from instead of just believing it 100%. So you don't need to be thinking about any of this when you're solving problems, but let's at least once see where those formulas come from. I'm going to start with a very small example of summing an arithmetic sequence, but just keep in mind that the examples are small because I want to illustrate what the formula is going to be. I'm not saying that you need to use a formula for this sum in particular. In fact, please don't. You already have a perfectly good way of adding those numbers, which is just add them. But even then, you probably have some mental strategies to add these things in a faster way and without having to write anything down or type them in your calculator, right? A very common strategy that we have is to try to match numbers that add up to round tens. So for example, 9 plus 21 is 30, and 12 plus 18 is 30, and 15 is just 15, which by the way is half of 30. But I'm only writing this down to show you. If I'm doing it in my head, I'm not going to write this down. I'm just going to look at it, imagine these numbers getting together in pairs, and I'm going to say, well, the answer is 75. That's a very good trick to keep in mind when you're adding a bunch of numbers that don't necessarily form a sequence. But it doesn't always work perfectly, right? So for example, in this one, I could think of 17 plus 23 is 40, and then plus this one is 60. But those ones are not really matching up in any convenient way. And even if they did, that's not a very systematic strategy. So strategies that are not systematic are rarely going to lead to a formula. A formula is a generalization of a strategy, but in order to generalize, it has to be done in the exact same way every time. So in order to do kind of the same thing that we did in the first example, maybe we should match the 8 with the 23, which is the first number with the last number, even though the answer is 31, is not a round multiple of 10. But let's keep going like this and see what happens. Oh, look at that. 11 plus 20 is also 31. And 14 plus 17 is 31 as well. Obviously, this was not a coincidence. I'm going to show you in general in a minute. But every time that it's an arithmetic sequence, this is going to happen. If you start from the outside and then you keep coming inside, these pairs of numbers are always going to add up to the same number, which in this case was 31. So one thing that you can do to quickly add an arithmetic sequence is to just in your head do 8 plus 23 is 31, and then you see how many numbers are in the sequence, which in this case is 6. You're going to be making pairs of them, so 6 numbers makes 3 pairs. 31 times 3 is 93. And that is basically it. That is the one trick for adding a bunch of terms in an arithmetic sequence. The only thing that I still have to do now is to generalize that and get away from just doing examples. I'll leave the example here on the top so that we can compare the general version with the example. But now as I start to write the general version, U1 is the first term of the sequence. And then what is the second term? Well, the second term can be called U2, but I don't want to call it that because then I would have a lot of variable names, U1, U2, U3, U4, and I don't want that. I want to have as few variables as possible. And the best way to do that is to use U1 and D, the common difference between the terms in the sequence, which in my example, D was equal to 3. And now I don't know what it is, and I also don't know what the first term U1 is, but I do know that the second term is U1 plus D. And then after that comes a third term, which is U1 plus 2D, and so on. Right now I'm putting dots here because I don't want to specify the number of terms in my sequence. I want to call it n, right? This will be the third variable in my list. I have U1, D, and n. But as I can't really write the appropriate amount of things without knowing how many they are, that's what the dot is for. And I'm going to start going backwards from the last term to the other side. The last term in my sequence is going to be UN, but I still want to write at least one more here before him so that I can match up some pairs like I was doing in the example. So because there is a common difference between terms, every time I move one term forward, I'm doing plus d, then it's also going to be true that when I move backwards, I'm doing minus d. So the term that comes right before un has to be un minus d. That's enough terms. That is completely general. This is not an example at all, so it will work for any arithmetic sequence that you have. The only thing that I still want to do here is give this sum a name. I want to call it S for sum, but I also want to indicate in the notation how many terms I'm summing. So I'm going to put an index in that as well and call it Sn. Now let's see if we can find a formula for that by generalizing the same strategy that we were doing in examples. So I'm going to match the first term with the last term of the sequence. Now I have no idea if that's equal to 30 or 31 or what, but I just know that it is u1 plus un. And this is the best part now, that when you move one term inside, so like the second from the beginning plus the second from the end, you're adding u1 plus d plus un minus d. So these d's are going to cancel out. Plus d cancels out with minus d, and this term plus this term is again equal to u1 plus un. That is why the numbers were repeating in the examples with a 30, 30, 30 or 31, 31, 31. It wasn't a coincidence. It has to happen this way because the sequence is arithmetic. Here, I don't know how many pairs I'm going to be making because I don't know how many terms there are. So I'm just going to put a dot, dot, dot there. But I do know that every single pair that I make is going to add up to u1 plus un, because the next one is going to be u1 plus 2d plus un minus 2d, so the 2d's also cancel out, and it keeps going on that way. Maybe you're asking what happens if there is an odd number of terms here, but that's not going to make it stop working. Remember, the first example we had 5 terms, and the middle term was 15. So if there is an odd number, you can just pair it up with itself. It's going to be 15 plus 15 equals 30 anyway. It doesn't matter if it's odd or even. The formula is going to be the same. So what is the formula? You take that total of the pair, which was like the 31 in the example, 8 plus 23, and then you have to multiply this number, which is this number down here, you have to multiply it by the number of pairs that you're making. Up here I had 3 pairs because I had 6 numbers. Here I have n numbers, so that's n over 2 pairs. And that, you can go check in your formula booklet, is exactly one of the formulas for the sum of an arithmetic sequence that you have there. Now, there is also another one, but it's actually the same formula. Let me show you how. Because we also know how to find un from u1 and from the common difference, right? You just start with u1 and then you add the common difference the appropriate amount of times to get to un. That's also a formula in the booklet. And this comment pretty much goes for any formula, but you don't need to look at this thing as if it was just a scary sequence of letters devoid of meaning, okay? This has meaning. To get to a term, you start from the first term and add the common difference the appropriate amount of times. This one is actually quite easy to memorize. But what I want to do with it right now is not to memorize it. I want to take this, which is equal to un, and I want to plug it into the other formula where it says un. So now it looks like that. You can see that it has 2 u1s, but that's why I changed the color. The first u1, the one that is stayed black over there, is the u1 from the sum formula when we take the first one and add it to the last one. But the red one is just coming from the substitution that I did for un for the last term, because un was equal to that, so there is another u1 there. So now I have 2 of them, and the colors obviously don't matter, so you can put them together. And that is the second formula for the sum of an arithmetic sequence that you have in the formula booklet, okay? You have both of them right next to each other. Now, it's a very common question for students to ask, why do I have 2 formulas? And also, which one should I use? Well, the answer is that which one you should use depends on the problem. I'm going to give you 2 examples now. It depends on what information the problem is giving you. And actually, that's why you have 2 formulas, because depending on the situation, one will be easier or the other one will be easier. So there's 2 to make your life easier. Here's the first example that I'm going to give you. An arithmetic sequence of 30 terms begins with 7 and ends with 43. find the sum. Now, notice at first that these numbers are not exactly friendly, because if you're going from 7 to 43 in 30 terms, then the common difference is probably a fraction. It's not an integer. I chose these numbers like this on purpose to show you that it doesn't matter. What matters is the information that the question is giving you. So let's check that out. 30 terms is the number of terms in the sequence. That's n. Begins with 7 means that u1 is 7. And ends with 43 means that the last term is 43, so un is 43. That's the information that the problem gave you. Now what's it asking you? Find the sum. So Sn is the thing that he wants you to find. Now what do you have? You have n, u1, and un. If you were to use that formula, you don't have everything that you need. You have n, and u1, but you would also need d, the common difference. And I was just mentioning how in this particular example, the common difference is probably going to be an ugly number. So in this situation, you don't want to use that formula. Let's try it with the other one. I need u1, which I have. I need un, which I also have. And I need n, that I also have. So that's perfect. In this example, I'm going to use this formula. Just plugged in the numbers in the appropriate places. And continuing the calculation, the answer was 750. Now for the second exercise. An arithmetic sequence starts with 7, 13, 19, 25. Find the sum of the first 20 terms. So he's asking about 20 terms. This is giving us that n equals 20. It's also giving us that the question is find S20. But what other information do we have? We have the first few terms of the sequence. So U1 we have. U1 is 7. We don't have the last one though. We don't have UN or U20, which would be the last one that we're interested in. Of course, we could calculate it if we figure out what the common difference is and then use the formula for calculating the 20th term. But we don't have the common difference either. What we do have is that U2 is 13. So when you put those two things together, you figure out that D equals 6, right? And you can use the third and the fourth term to check that as well, putting that on the list of information that I have. Of course, you could, now that you have that, go on to first find U20 and then plug all of these things into the first formula that you used. But there is another way. You don't have to find U20 because look at what this formula is asking you for. U1, I have. D, I also have. And N, I have as well. So for this problem, for this context, this set of information that he's giving me, that formula is going to make it easier than this one. So you just plug in the numbers in the appropriate spaces in the formula, carry on the calculation, and find the answer. And this also works if the problem is asking you for something else that is not exactly find the sum, right? In this one, he's asking me to find the common difference. So what he wants is D. Now, even before I read the rest of the problem and figure out what information I have or don't have, I can already choose which formula I'm going to use because that one has a D. This one does not. So if I use this formula, I can probably do more steps and use the other formula together with it to find some way to get to D, but that's going to be more work. It's definitely better in this situation to choose the formula that already has a D and to try to fit numbers to the other variables in there so that I just get an equation in the variable D. So what do I have here? The sum of the first 15 terms. So this is telling me that n equals 15. Of an arithmetic sequence that starts with 8. This is telling me that U1 is equal to 8. Is 100. Wait, what was the beginning of that sentence? The sum of blah, blah, blah is 100. So he's telling me that the sum is 100. The sum of 15 terms is 100. So I already have the left side of my formula here. It's going to be 100 equals, and then the rest of the stuff. So I'm putting an 8 here because U1 is 8, and the formula begins with 2U1. Now the next thing in the formula is D, and for that one I'm not going to be able to plug in a number because I don't have a number. That's exactly what I'm looking for. So I'm just going to leave it as D. But then n minus 1 I think I know because n is 15. So n minus 1 is 14. And finally, I have to multiply all that by n over 2. Again, n is 15, so I'm going to put a 15 over 2 there. And now the only thing that you need to do is to solve this equation for the variable d. Notice how everything else has become numbers, so that means that you can find d in this equation. Of course, there are many different ways that you can do this. I am going to start by multiplying both sides of the equation by 2 because I don't want to have that fraction over there. And I've already done the 2 times 8 is 16 here as well. I guess I could do distributive here now with the 15 going to the 14d and the 16, but I'm kind of scared of 15 times 16. It seems like it's going to be such a big number. So instead, I'm going to divide by 5 first, both sides of the equation. That's better. 200 divided by 5 is 40. 15 divided by 5 is 3. Now I'm going to do distributive with just the 3. And then I ran out of space in the camera down here, but you can finish this one, right? It's almost ready. And now I want to kind of do the same thing for the geometric sequence. But the reason why I'm choosing to go straight to the general version here instead of starting with a small example is because it's very difficult to make a small example with a geometric sequence. It just grows so fast because you're multiplying by a number, right? So multiplying makes it go bigger faster. For example, if you start with 2 and then multiply by 2, you get 4, 8, 16, 32, 64, 128. It just gets very big very fast. And if you wanted to not do that, then you have to choose a weird common ratio between the terms, like 1.1, for example, which will be very useful in the future for certain applications, but then we're going to be using a calculator, right? Not for writing by hand like this. So anyway, here is a geometric sequence. It starts with the term u1, and then every time that it moves a term, it multiplies by a common ratio that is q. So here it has been multiplied by q only once. Then I take the u1 q and multiply it by q again, making it u1 times q squared, and so on and so forth, until I get to this last one over here, which is un, but I don't want to write it as un. I want to just keep it as u1 times q, 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 n minus 1 times, right, to get to the un. Just follow the steps here because this one is a little bit trickier than the other one. This is not the kind of thing that you would be expected to think of by yourself at all. It's just a pretty thing that I'm showing you that's going to lead to a formula that you're going to use. But I am going to start by taking this equation and multiplying both sides by q. Maybe you are not thinking of this as an equation because we are not trying to solve for the value of any variable here. And that's true. But it can still be treated as an equation because it has an equality sign there, which means that I can do the same operation to both sides, just like I would do if I was trying to find the value of something. So the left side here is boring. I had Sn and now I have QSN. What's going to be interesting is what happens on the right side, because most of these terms already have Q, except for the first one, which is going to become U1Q. But the other ones that already have a Q, they're going to get an extra q. So for example, u1q times q is u1q squared. And that is going to happen to all of them. Everybody's going to get an extra q, which means that the exponent of that q is going to go up by 1 for every single one of these terms. Now I've written those orange arrows here to show you which term is coming from which term, but they haven't changed the order, right? They're just in the same order that they were. And each exponent has become 1 bigger than it used to be because of this multiplication by q that happened on both sides of the equation. But what I want to do now is I want to take this whole thing here and I want to just pull it to the side. So this is what it looks like now. Notice that one of the terms that I had on the bottom line, which had the u1, q3, is now hiding inside of the dot, 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 but the arrow is here to show you that it is still there. And conversely, this term here on the second line with the q to the n minus 1 was previously hiding inside of the dot, 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 but now it is appearing here. And you can see kind of that it came from one of the terms that is hiding in the dot, dot, dots on the first line. But the really interesting thing that I want you to see now is that I am going to subtract the first line minus the second line. And this can feel a little bit stranger because usually when we do the same operation to both sides of the equation, like subtracting 3 from both sides, it's minus 3 and minus 3. So you're subtracting the same thing, right? So now it can feel like you're subtracting different things from both sides, because over there I'm going to subtract this thing, and on the right side I'm going to subtract this other big thing. But they are the same thing because they have an equal sign between them. So if I subtract 3 from one side and 2 plus 1 from the other side, that is still 3, right? So I am allowed to do that. I can take two equations and subtract one from the other. So I'm hiding the orange arrows for now because there was too much stuff here. But let's see how we're going to do this subtraction. We're going to do it term by term. So you can see, for example, that this minus this is going to cancel out. But there are some things missing here. So for example, there's nothing underneath this one to subtract from it. But that's okay because I can just pretend that there was a 0 plus something something here, and adding 0 is always allowed because it does nothing. And for the same reason, I put a plus 0 on the top there as well because I want every term in one line to line up with the term in the other line. So let's see what else cancels out. U1 Q2 minus U1 Q2. These two are also the same, so they're going to cancel out. And I hope it's not difficult to believe that everything that is inside of the dot dot dots is canceling out as well, because this comes in a very strict pattern. Even though you can't see it, you know what's in there. So let's see what we have left after canceling out almost everything. On the left side of the equation, we have Sn minus Qsn. On the right side of the equation, we start by seeing u1 minus 0, which is just going to be u1. And then a lot of things that cancel out except for the last one. The last one says 0 minus that term. So I'm just going to put a minus the term over here. There was a little typo up there until now. Okay, I've just fixed it. If you didn't notice it, it's fine. It's correct now. So now I have this. Well, that looks ugly. That's a lot of letters. I think I need to take a step back and remember what I was even trying to do in the first place. I had the sum of a geometric sequence, and I wanted to figure out a formula for Sn. Of course, I want it to be a small, compact, usable formula, right? I don't want to just write Sn equals u1 plus u2 plus u3 plus u4 because that's obvious and it's not helpful at all. But what I have here is still not what I want. It's shorter, so it's doing the compact thing, but it's not really looking like a formula for Sn yet because Sn is not isolated in the equation. That's the only thing that's left for us to do, is to isolate Sn in this equation. So I'm going to start by factoring it out of the subtraction here. Notice that I've put the 1 times Sn there to help that. From this side, I can factor out a u1 because there's also a 1 times u1 here. And now the only thing left to do is to divide both sides by 1 minus q. And that's it. That is the formula for the sum of a geometric sequence. I'm not really sure if this is the way that it appears in the formula booklet or if he has multiplied the numerator and denominator by -1. Maybe he even has both versions in the booklet. I'm not really sure. But this is what the other version looks like, right? After you flip the signs of both sides of the fraction. Just so you know, both formulas are exactly the same, as they have to be because one came from the other by just making an equivalent fraction. But it might be more convenient to use this one if you have a value of q that is bigger than 1, and to use this one if you have a value that's smaller than 1, such as 0.2, for example. And here would be like 3. Just because you don't want to have a negative number in a denominator. It's a silly distinction, and it really doesn't matter if you do it the other way. Now let's do a couple of examples here. Like I've mentioned, you're going to choose which of the two formulas to use depending on whether the ratio of your geometric sequence is bigger or smaller than 1. Not that it's going to make a big difference if you happen to choose the other one. So some examples are going to just tell you the value of the common ratio, so you can use that information. But sometimes the exercises give you the information in a different way, as this one, for example, which instead of giving you the ratio is giving you two terms. In this case, you can be sure that the common ratio is actually smaller than 1 because this sequence is decreasing. The first term is 25 and the fourth term is 3, so they're getting smaller, which means that they're being multiplied by a number that is smaller than 1. For that reason, in this exercise, I'm going to use this formula. And this is the way I'm going to decide which formula to use regardless of what the question is asking me. In this case, it's really asking me to find the sum, but you know that sometimes the problems are backwards and then they give you the sum and ask you to find something else. but that doesn't matter. So I'd like to start this exercise by substituting the information that I have into the formula, but I don't have the common ratio yet, so I have to find that first. And I am going to use my calculator for this question, but it's important to remember that having a calculator is not magic. It doesn't mean that the questions are automatically easy because you have a calculator. You still have to know what to put into the calculator. So in this case, I was given the first and fourth terms, and I know that the relationship between those two terms is this. First term gets multiplied by the common ratio 3 times in order to get to U4. So I can substitute the numbers that I have into this equation. And yes, most calculator models that you're going to be using have an automatic way to type it this way and get to the value of Q. And sometimes that's very valuable if you have a very complicated equation to work with. I just don't think that this is the case. I think that it's going to be more work to find how to do that in the calculator than to do a little bit more here by hand and then just type a calculation instead of typing something to get the calculator to solve an equation, because those things are very different. So with a little bit more manipulation into solving the equation here, I did a couple of steps to make the Q the subject of my equation. Now I just have to ask my calculation for the value of the cubic root of 3 over 25, which is a very straightforward thing to type, and then I've written my answer here in 3 significant figures. Now I get to plug in the things that I wanted into the formula. So it looks like this. U1 was 25, that's Q, and N is 15 because I am looking for S15. And then that's another calculation to put into the calculator. I just typed this whole thing to get to this number down here. A little bit of an interesting coincidence here that S15 is almost exactly 100 times Q. I don't know why that happened, but I do say almost the same because I'm writing my answers to 3 significant figures, and when I look at them in my calculator screen, they're not exactly the same. Which reminds me to tell you that also as I was typing this thing, I did not type 0.493. I put a lot more stuff that I had in my calculator. That's okay to not put it on paper. In fact, it looks better if you just write down 3 significant figures. But when you're continuing a calculation, it's always better to use more significant figures because it creates a little bit of a difference in the answer that in this case I don't think mattered because the difference was in the 4th place here. But sometimes it does make a difference, and you can lose a mark in a very silly way just because of accumulating approximation errors. And also personally, when I type a long calculation like this, I like to type the whole thing at once, but not everybody likes that. Some people like to do it step by step, like maybe they would do the 0.493 to the power of 15 first, and then see what number that is, and then do 1 minus that number. That's okay as well. It's a different process. But if you're doing that, just be aware that you have more opportunities for approximation errors. So be sure to track more than just the 3 significant figures that you want. On the other hand, if you're doing it the way that I'm doing, which is to type everything at once, there is a different kind of opportunity for error that you have, which is the order of operations. You have to type all of the parentheses that are necessary in order for the calculator to understand what you want. For example, the denominator here, we don't write it on paper with the parentheses, but in the calculator we do need to put that parentheses because otherwise it will just be dividing by 1, which is the same as doing nothing, and then subtracting this from a different number. It's going to be a wrong answer. But anyway, those comments about calculators are general to whatever you're doing in the calculator. They're not specific to sequences or sums of sequences or anything like that. So let's get back on track and do our next exercise, in which I do have an increasing sequence this time, but I chose to give you the information in a different way. I gave you a term and the common ratio. So the common ratio is 1.3. It is bigger than 1. You know that the sequence is increasing, but what you really care about right now is that probably you want to use this formula instead of the other one. Just to make sure that you're paying attention, I did not give you the first term. I gave you the second term, but you're going to need the first term to put in the formula. So how are you going to find that? It's the exact same process as we did in the previous exercise, but this time we do have the ratio and we are trying to find the first term. The previous exercise was the other way around. But that's the nice thing about formulas, is that you can use the same formula to find different pieces of information. The formula is relating three different quantities, in this case U2, U1, and Q. Any two of them that you have, you plug into the formula to find the third one. That's what makes formulas so convenient. And in this case, it was a simpler calculation. I didn't need my calculator. U1 is 20. So now let's plug what I have into the formula. And this time, the thing that I don't have is n. I am trying to find n. And that's the exact same comment as I just did about the other formula. The formula starts with Sn equals, but it doesn't have to be used to find Sn. You can use the same formula, having Sn, in order to find something else that you still don't have, something else that appears in the formula, which in this case could be U1 or Q or n, provided that you have Sn. And the wording of the problem is something that I want to talk about, but it's almost like Sn is equal to 1,000. So I am going to put equals 1,000 here. It's not exactly equal because he does say that it's closest to 1,000, which means that there isn't going to be a value of n that makes that sum be exactly equal to 1,000. But he's looking for the value of n that makes it closest to that. So the strategy that I'm going to do is to pretend that I'm looking for an n that makes it exactly equal to 1,000. It's not quite going to work in terms that I'm going to solve this equation for n here, and I am going to find a value that is not integer, which is not possible. It's not a valid value for the index of a sequence, right? It has to be S3, S4, S5. It can't be S3.7. That doesn't exist. But then after I've done that, I'm going to work with that and see what I can do to get the precise n that is closest to 1,000. Before that, we do have to solve this equation, this one here that I've circled in red. And again, you probably could use some function in your technology to just type this complicated thing and get the value of n. I am much more comfortable working by hand a little bit, as long as I know that I am not making mistakes in that process of doing by hand. That said, I am recommending you do this if you are confident that you are not going to make mistakes. Otherwise, please spend the time typing. It is worth it to get the right answer. For example, in this kind of situation here, I see a lot of people multiplying 20 times 1.3, especially since that's a kind of easy calculation that we've gone through before in the same problem. The answer is 26. But you're not supposed to multiply the 20 by the 1.3, because if you look at it from the point of view of the 1.3, a lot of stuff is going to happen to him before he gets multiplied by 20. There is an order of operations. So let's look at the 1.3. The first thing that is going to happen to him is that he's going to get to the power of n, then it's going to subtract 1, then divide by this other thing here, and only then is it going to be multiplied by 20. So there is an order of operations, and you can't really forget that it exists. I know most people don't get the order of operations confused. They don't like suddenly start thinking that plus comes before times or something like that. That's not what happens. The reason for the mistakes is a different reason. It's forgetting that the order of operations needs to be obeyed in every single situation. It's not something that counts sometimes but not other times. No, it's all the times, including this one, including when you see a 20 times 1.3 right here, but there's other operations going on, so you do have to obey the order of operations. So the first one that I did was the denominator, which was just 1.3 minus 1 equals 0.3. Now I'm going to multiply both sides of the equation by 0.3 to get rid of that fraction. And notice that when I did that, I chose to write a parenthesis here explicitly that wasn't written before. I mean, it wasn't written explicitly, but it was there because that was the numerator of a fraction. So that makes it automatically happen first before the division. But now that I've multiplied by 0.3 and I don't have a fraction anymore, the parentheses become necessary to be there explicitly because there isn't anything else in there representing that change in the order of operations. Because we do want this subtraction to happen before that product. It was happening before the product ever since the beginning, so it can't change in the middle. Anyway, the next step that I took was to divide both sides of the equation by 20. And now I don't need the parentheses anymore because I don't have the product and the subtraction. I only have the subtraction. Now I'm going to add 1 to both sides of the equation. And now is the point when I'm going to use my calculator because there is no way around it. In order to get a variable out of an exponent, you have to use the log. And by hand, the log is always either obvious or impossible. So if it was a 2 instead of a 1.3, 2 to the power of n is equal to 16. I don't need a calculator. N is 4 because 2 to the power of 4 is 16. That's the obvious version. Now, the impossible version is anything else, right? 1.3 to the power of what is 16? I don't know. Let's ask the calculator. 10.6 in 3 significant figures. I am looking at the calculator screen and it's actually 10.5677 more digits. But on paper, you only have to write this down. Now, remember what we were talking about. 10.6 or 10.56 is not a valid value of n, which is an index of a term in a sequence. But what we were looking for also wasn't a term that makes it equal to 1,000, which would be the 10.6. We're looking for the one that makes it closest to 1,000. And this is very suggestive that the answer is going to be 11. But in order to make absolutely sure, I do recommend that you calculate S10 and S11. I just got those two numbers by plugging in n equals 10 and n equals 11 in the same formula. And you can see it's a very close call because neither of them are particularly close to 1,000. But S11 is actually a little bit closer because it's only 128 units away from 1,000, while this one is 148 units away from 1,000. So S11 wins. But do calculate both because with geometric sequences, you never know. The growth is not linear just from the index being closer to 11 than to 10. I'm just saying it's not as clear. So just to be safe, try both of them in the formula and give the answer. Now, something that is related to that, but it's not exactly the same, is that sometimes in these questions, some students choose to skip the whole thing and just plug numbers into the formula at random until they find the closest one. In this case, because the answer was 11, is a very small number, it wouldn't even take that long to do that because you can type the formula once for a number and then just copy paste to try it again with different numbers. Eventually you're going to get there. Even if the answer was bigger, if it was not 11, because you don't have to go one by one, right? You're smarter than that. If you see that it looks like it's going to take a long time, you can skip a few numbers. If you see that you've gone too far, you can come back. There's all these sort of strategies that are technically valid and they do lead you to the correct answer, but I really wouldn't do that in an exam. Because an exam is not a situation where you're trying to find the correct answer. It really isn't. An exam is a situation where you're trying to display your knowledge. Finding the correct answer in the end, sometimes it's just going to be the smallest part of the marking. It's going to be the final 1 mark, and there's going to be a ton of other marks for process. So while in real life, I would be probably interested in the final answer because this would have come from a situation that I'm interested in. So yeah, that trial and error strategy, why not? It's fine. But just remember that. And I'm going to say it again because I think this is very important. An exam is not a situation where you're looking for the correct answer. An exam is a situation where you're looking to display your knowledge. And trial and error in a calculator does not require a lot of knowledge. That's not supposedly going to get you a lot of marks. This displays knowledge. What you want is to display that you know the content. Getting the right answer is a consequence. It's not the most important thing.